First off, what are optical isomers? They share the same formula, the same connectivity, but different spatial arrangements in 3D space. This comes about because of what's called an asymmetrical center, a carbon bonded to 4 different groups. So this would constitute my asymmetric center, what they call a chiral carbon. R here represents different radicals. They could be hydrogen, a halogen, a carbon chain, and or even a functional group. Here would be its isomer, its pair. These two do not share the same 3-dimensional arrangement. They're not superimposable. They don't fit one upon the other. I've employed here a convention to show coming in and out of the plane of the screen. The dashed lines represent going into the screen and the solid wedge out of the screen. These images are mirror images of each other. The name we give to this is enantiomer. Let's look at an example. Here I have a chemical formula, and the first thing I would like to do is identify the chiral carbon, the carbon which is bonded to 4 different groups. And this would be it. If I check, it's bonded to the methyl group, it's bonded to a hydrogen, it's bonded to a chlorine, and a carboxylic acid, my 4 different groups. So it would perhaps have this structure, with my chiral carbon being located here. To construct its mirror opposite, I imagine a mirror in this place and then provide the reflection of it. This would be its optical isomer, or enantiomer. Optical isomers share an activity and ability to rotate the plane of polarized light. Here's what I mean by that. We have light that's polarized, coming through a polarizing filter, coming upon our sample that contains one of the enantiomers. The plane of that is shown here in the green. Once it passes through that plane has been rotated or moved by a certain number of degrees. My example here is it moved at 5 degrees to the right. If I was to employ its optical pair, it would rotate it 5 degrees to the left. A mixture of both of these enantiomers, a 50-50 mixture, is called a racemic mixture. Let's look at a question. Draw the possible structure of C5H9Br that doesn't have cis-trans isomerism but is optically active. First off, let's look what we have to do to make it not have cis-trans isomerism. I'm going to begin my carbon chain with a double bond and hydrogens located on both of them. That therefore removes the possibility of cis-trans isomerism. Now, to make it optically active, I need to look at that chiral carbon. I've decided to make the 3rd one in the chain the chiral carbon. You could use the 4th as well. So I'm going to attach to it now what remains in my molecule, so I have 4 different groups, the bromine and an ethyl. Let's count the number of constituents again. So I have an ethylene radical, bromine, hydrogen, and ethyl. That makes 4 different groups, hence it's optically active. I hope you found that useful. Thanks for watching.